It, it, it.
Otherwise, permanently some line is there. Hmm? I got it.
You, 4 years.
Yeah,
No, 2 hours. 3.
yeah, and the yeah, we are there.
No, 2 years. 3 hours.
Hmm. So is it audible now? Ah, yes. Right is there.
Slowly to
Hmm?
slowly to push to name your laptop.
Okay.
Chat. स्क्रीन शॉट वो ना थिएटर मोड में है यूट्यूब पर अभी
Any introduction here? इसका कोई इंट्रोडक्शन वगैरह?
स्टार्ट करने
Hmm.
नहीं वो अपने हिसाब से बस 1 मिनट 2 मिनट और वेट करते हैं इसमें 459 लिखा रहा है
So registration is 1,051. No, I'm not
No,
noticed.
no, YouTube, YouTube.
YouTube.
No, if you are able to see the starting,
So here you
so
can see.
there was
Ah, if I use my own, then I become another wrong user. I don't want. Ah, this should come here. Group chat. वो on चाहिए.
चैट मैसेज ग्रुप मैसेज करें जैसे हेलो से एवरीवन मुझे भी सुनना
Then only I can able to make out. Or I'll again no, no, I can go.
सर्विस करने के लिए बोले ना ऐसे कंपटीशन लाइन स्टार्ट कर Yeah, which again? Which is it's not really clear. Maybe high liquid is
So there are many people in the website here.
how you can start.
Ah.
It's already like
So good evening to everyone, and I'm quite happy to give a live session for our course Stochastic Processes. And already there are two students are online. I'm seeing the words also. Hello sir, hi everyone, good evening, hello sir, and so on. Happy about that, and seems around 1,000 students registered in this course. We are running this course a third time. We started with the 20 hours course, then we land up 40 hours course. And now we are running this course with my partner, Professor Yan Selvaraju from IIT Guwahati. And already four or how many, six? Yeah, this is the sixth week the course is going on. And whatever the queries you type it, and I can see it in my screen. So I can answer the queries, whatever you ask, the technical things. Please.
in the course.
Uh, yeah, one student asked the query. Let me read out the query. Examples of a stochastic process by Mahendra Singh Rautila. There are plenty of examples for stochastic process. It's possible. Stochastic process is basically a collection of random variable on a probability space. Therefore, whenever you come across a collection of random variable, then we can always think of that as a stochastic process. For example, um, number of cars entering into the main gate of your institute. Whatever the institute you think of, how many cars are entering to the main gate of the institute over the time. That means at every time you will find how many cars are entered. That becomes a random variable, and those are going to be numbers starting from either 0 or 1 or 2 or 3 and so on. Therefore, for every fixed time, you may land up with one random variable, and over the time, you will have a collection of random variable in this random experiment, and then this follows a one stochastic process. This is only need not be only one stochastic process for this random experiment. You can create some other random variable that form another collection, and then you can land up another stochastic process also. For example, you started counting how many people are leaving from the institute over the time. So the departure, number of people going out from the campus, that also follow another stochastic process. There may be a dependency over one collection of random variable with another collection of random variable. You can discuss the dependency in many ways. So, for a given random experiment, you can always have a many set of random variables, and each set or each collection of random variable going to be called it as a one stochastic process. Like that, you can have a many more stochastic processes in a given random experiment. I can think of another example. In a class, uh, how many students are coming from the different state of India? That becomes a random variable. In that case, since the number of states in the country is a finite, therefore you will have a finite number of random variables, and that form a stochastic process. In this collection, it has only finite number of random variables. That means, I'll repeat, number of students attending in my course from different state of the country, that becomes a collection of random variable, and that becomes a stochastic process. Another example, the money I have in my packet in a day, that's a random variable. So I can think of making a collection of random variable like how much money I have it in every day. So each day is going to be a one random variable, and that collection is going to form a collection of random variable. That's also stochastic process. I hope I have given more than two examples to understand how the stochastic process comes into the real world. Yes, the another query. Yeah. Yeah. So one student was asking, hope you are enjoying the course
So
of
this
the
we have this.
online. Okay. Marco chain process. I started to do two courses. One is programming language, and one is speaking. Okay. So let me give an example of Marco chain process. Even that word is not that sentence is not correct. Let me explain through the tablet about the Marco chain and the Marco process. One. So consider the stochastic process x of t greater than or equal to 0. So this is a stochastic process. Oh, I have to share the screen then only. Please wait for a minute. Ah, yes. Correct. So, so it's not visible there.
No, it is good.
Okay. Yes. So x of t, that is a stochastic process. Okay. Whenever, so for in this case, this stochastic process x of t, the parameter space t greater than or equal to 0, I made it. So parameter space could be discrete or continuous. So I can classify the stochastic process into the form of Markov process whenever it satisfies the Markov property. So any stochastic process satisfying a Markov property, then we call it as a Markov process. So here I am not making any assumption over the parameter space has to be discrete or continuous, state space has to be discrete or continuous. Any stochastic process satisfying the Markov property, it is going to be called as a Markov process. Maybe I can rewrite this instead of t greater than or equal to 0. T belonging to capital T. So that way it is very clear. So this is a given stochastic process having the Markov property going to be called as a Markov process. Now, if the state space, the S which we discussed, capital S, that's the notation I'm using in most of my classes. Capital S is a state space. That is nothing but the collection of all possible values taken by the x of t or t belonging to capital T, the state space. When the state space is going to be discrete, that means the number of elements in the state space is going to be finite or countably infinite. Then we call it as a state space is discrete. When the state space is discrete, then we call this Markov process as the Markov chain. So the Markov chain comes from the Markov process with the assumption or with the state space is going to be discrete. After we land up Markov chain, now I'm going to classify based on the parameter space whether this is going to be a continuous time Markov chain or a discrete time Markov chain. Therefore, I can move to the next slide. Yes. So now I have a Markov chain. Markov chain based on the parameter space capital T. Earlier, based on the state space, I made it as a Markov chain. Now, after the Markov chain, based on the parameter space is a discrete or continuous. Discrete, I said already. That means the possible values are going to be a finite or countable infinite. Continuous means the possible values of capital T, that is going to be uncountably many. When the T is going to be discrete, we call it as a discrete time Markov chain. When the parameter space is continuous, we call it as a continuous time Markov chain. If I'm making any mistake, please raise the question, therefore I can fix it immediately. If at all I make any mistakes. So from the stochastic process with the Markov property, it is called a Markov process. When state space is going to be discrete of the Markov process, is going to be called as a Markov chain. After that, when the state space is, when the parameter space is also discrete, then it is going to be called as a discrete time Markov chain. Otherwise, it's a continuous time Markov chain. So the examples of CTMC, the Poisson process, every time we discuss that is a continuous time discrete state stochastic process having the Markov property, therefore it's a Markov process, and it has a state space is a discrete and parameter space is continuous, therefore it is a CTMC. And later, whenever it has the birth death property, whenever the Q matrix is a tridiagonal matrix of the CTMC, we call it as a birth death process. So this is going to be a special case of birth death process, and this is going to be a special case of pure birth process, that is a Poisson process. I can give you the another example for Markov process that is the stochastic process with a continuous time, continuous state satisfying the Markov property. That's basically a Markov process. As an example, we can give a Wiener process. Wiener process has a Markov property and the parameter space is continuous, state space is continuous. So this is a good example of Markov process. Whereas the discrete time and the Markov chain, that is going to be discussed in a different way because the state space is discrete. Therefore, in the statement you made it a Markov chain process. That's a wrong statement. Either we should use a Markov process or Markov chain. There is no Markov chain process. I think I have explained those things, but still the Poisson process, birth death process, CTMC, that is going to come in the further weeks. Right? Yes. If at all any other question, if we have. Yeah, there's another question comes from the live session. Let me read out the question. Yeah, the first question was examples of stochastic processes that I have answered. The second question is let me go back. How to go back? Ah, yes, I'm back. So the second question, let me read out. In the concept of conditional probability, you are discussing about reduced sample space. Could you please brief it once again? Basically, the probability part is a review of probability. So you can always go through any standard books for reviewing the probability part. And the question raised is discuss about the reduced sample space. Let me recall first what is sample space. Sample space is the collection of all possible outcomes of a random experiment. All possible outcomes. That is very important. You can take a few possible outcomes and say that it's a sample space. So sample space is a collection of all possible outcomes, and sometimes in a random experiment, some of the outcomes would have been already taken place. Now the situation is what is the probability of some event given that something already happened. For example, you think of writing exams. In that exam, you have suppose you assume that you have two small exams. We call it as a minor one, minor two, and we have a 2 hours exam that we call it as a major exam. And even though what is the grade you are going to get at the end of the semester for that particular course, after minor one marks is released, you may have the question of what's the chances of getting this grade given that you got this many marks in the minor one exam. Not only that, similarly we'll go for what will be my grade at the end of this course, given that I have already scored this many marks in the minor one marks, this many marks in the minor two marks. So this is a sort of examples for conditional probability. In that case, the earlier ready original probability space which you have created no more going to be useful when you want to find out the conditional probability. There are two ways. Either you can go for the by definition. Still, you can keep the original probability space, find out the suppose you are interested of probability of some event A given event B, and the event B already has a positive probability with that condition. You can find out by using the definition, you can find the proportion of probability of A intersection B divided by probability of B. Otherwise, you can do the second method. You can identify the reduced sample space. From there, you can find the probability of A in that. You don't need to use a formula. So, the reduced sample space is nothing but a collection of possible outcomes which is going to give the probability of B is going to be greater than 0. So, you collect those possible outcomes that will form a reduced sample space which is corresponding to the event B, which is a reduced sample space. Then after that, you can find out the probability of A, which is contained in that those collection of possible outcomes that will form a event B. So I'm just giving one example, but if you go through any of the standard probability book, there are many more examples to discuss conditional probability. Two ways of finding the conditional probability. One is by the definition, the other one is by the reduced sample space. Still, if you have any other question, that will give us. So, are you satisfied with the answer which I have given, so that I can move further or and further some other questions? The other question raised by the forum or the C5. What is the sojourn time in a state in a discrete time of coaching, like we have a exponential distribution for CTMC? The CTMC part comes later. Sorry. So for the DTMC, that is a discrete time of coaching, the sojourn time, that is nothing but how much time the system spent in a state before moving into some other state. That we call it as a sojourn time. Sojourn means the time spending that particular state before going into some other state. And since it is a discrete time Markov chain, the time spending in any state is in the form of 1, 2, 3, and so on. Therefore, by using a Markov property, you can find out, that's a separate exercise. some of the books they have that as a exercise problem also. So if you work out the way the proof of the sojourn time of a CTMC is exponential distribution, the same way the similar proof we can do it with the discrete time Markov chain, and finally you land up the form of geometric distribution. That means that the sojourn time in the discrete time Markov chain for any state is going to be geometric distributed with the parameter as a function of that particular state that can be proved. And if you need the proof, we can provide it later stage also. And intuitively also one can visualize since the system is moving into the different state with the Markov property, therefore the future depends only on present, not on the past history. Therefore, each step is going to be considered as a Bernoulli trials. Each step the system is staying in the state is going to be a Bernoulli trial with the probability of success being in the state minus the probability of system is moving into other state and so on. Therefore, because of the Markov property, you can visualize the system is keep spending one more step in the same state without moving into some other state and so on. So that follows independent Bernoulli trials, and the first success is going to be considered as the moving into other state. Therefore, in this scenario, we should consider moving to the other state is going to be a success, and being in the same state is going to be considered as a failure, probability of failure of a Bernoulli distribution. So it is going to be n minus 1 Bernoulli distributed independent for failure, and the success is a multiplier succeed to the other state, therefore it follows up. So what I am saying is that it is similar to the how the geometric distribution is formed with the n minus 1 independent failure events and followed by the nth event as the success event. In the same way it happens, therefore this is going to be a geometric distribution. Any other question? Any other question you can type so that I can answer. It's good that we are able to see 21 viewers in this live session. So, when you are solving the assignment sheets, you put a lot of effort. Therefore, when you write the exam, that will be very useful. And if you have any doubts while solving the assignment problems, you can raise the question to our TAs. They will answer. So that way we will know where we are lagging or which information which we have not provided that can be given. And since it is a online course which is different from the regular course which we teach every semester, or alternatively I'm teaching the same course, therefore I know what the students doubts and how to clear it. And since it's an online course, I may not know whether you have a difficulty to solve some particular problem, so that can be asked to the TAs or to us, then we can fix it. Yeah, somebody was asking what is weak sense stationary and strong sense stationary. So basically, the random process or stochastic process are very well used in signals in electrical engineering. So most of the time, they need they capture the signals as they study the signals as a stochastic process, and So as long as it has the some stationary property, then studying the signals will be easier for them. So they look for whether the stationarity property is satisfied by the signals. And as a mathematical modeling, the the arrival of the signals or the signals comes that we can think as a stochastic process over the time. Therefore, so usually if it has a stationary property, then it is easy to study. So when we use the word stationarity, the English meaning of stationarity is a time invariant. Whereas here we are studying through probabilistic way. So you should combine the concept of probabilistic way as well as time invariant. In the probabilistic way means it can satisfy in the distribution level or it can satisfy in the moments level. So accordingly, one is going to be called as a strict sense, the other one is going to be called as a wide sense. So strict sense means the time invariant property is satisfied in the distribution level, the probability distribution. That we call it as a strict sense stationary. That means the way you pick the signals at some arbitrary time and find out the joint distribution. If that is same as you shift the time scale by some amount of time, then you collect the signals of those time, then you find out the joint distribution. So if both the joint distribution, shifted one, non-shifted one, if both the joint distributions are same, that too for all the shift is a positive shift. So for all the shift this condition is satisfied, then we call it as a strict sensation. Usually don't happen. It is very difficult to have a stochastic process having a strict sensation process. Then why we study? We study because if this property is satisfied, then the behavior or the prediction of the signals or whatever the stochastic process having a strict sensation process will be studied easier. Is what we study. Actually, in many of the real world problem, it won't happen. But we can make this assumption and you can get the nice results or close form results with this assumption. Now I'm coming into the white cell stationary. So white cell stationary, that is a time invariant property with respect to moments. Here the moments means the first order moment is v and the second order moment is usually variance. But here we have a collection of random variables. Therefore, any two random variable, you look for what is the covariance. So if the covariance of any two random variable as a function of only that interval matters, not the actual time, then we call it as a byte sensation. But before that, the variance should exist for each random variable, and the mean has to be independent of, free from that parameter, and the covariance has to be in the length only, not the actual time. So if everything is satisfied, then we conclude it is going to be a byte sensation on reduce the. So there is a big difference between the white sense stationary and the stick sense stationary. There are some stochastic process may be a white sense stationary, it may not be a stick sense stationary process. There are some stochastic process may be a stick sense stationary process, may not be a white sense stationary process. So there is no different one if condition in both sides. There are some examples which may satisfy both. In our course, we have created some example as a cooked up example to show how this condition is satisfied. But the students are from electrical engineering. There is a course called the Signals and Systems. In that course, you will study more the theoretical background of signals that satisfies the stick sense stationary or right sense stationary. I hope I would have answered your query. Please. You write something, I can know that you listen and you got feedback from me, whatever I said. Sura, Shivaji plus. Correct? Any other question? Thank you, sir. Ah, okay, good. Yeah, since you asked, everybody is getting benefit. Therefore, we should thank you also because of you only everybody is getting one more explanation of this particular concept. Thanks to you also. Any other question? Let me check that. Yeah, whatever we are teaching is almost the introductory level that we should remember, and we have not lifted the course into the little higher level. The higher level courses are stochastic of finance. There's a course called advanced stochastic process in which more theoretical probability is used. So whatever we are using is, I won't say elementary, it's an average level. So there is an advanced level stochastic process course also. So the 10 topics which we are covering, almost all the 10 topics are in the introductory level. So you can always pick up, suppose you are interested in TTMC more, hidden Markov chain, hidden Markov model. There are many applied discrete time Markov chain problems are there in the books. So you can go deep into that by considering the TTMC part is as an elementary. Similarly, continuous time Markov chain. Similarly, the later part of the semi-Markov process or Markov regenerative process, they are very elementary. Uh, Similarly, the last topic I remember, branching process, that is also very, very elementary level. Whereas the current literature or the research work on the branching process is maybe 10 times more than what we have covered it in this course. So I would say this course as a elementary stochastic process. Any other question? Yeah, I asked my TAs also. Both the TAs are next to me, Puneet as well as Nitu. Uh, is it possible to show the camera people? You should say. Or you can come over. You can come over. Yes, she's Ritu Sharma and yes, he's Puneet. Yeah, any other query or if anything I missed it, tell me. Ah, yes. So application of okay. What are all the my TA is making a question? What are all the benefits of this course? This course immediate application is the finance. So suppose you are interested in financial mathematics, in particular it is a quantitative finance, then the knowledge of a stochastic process and stochastic calculus. That's also few levels. Yes, so we have more than 2 weeks of lectures on the stochastic calculus part. So that will make you uh, good understanding of stochastic concepts which are related to the financial mathematics. So that's a major current trend of need. And other than that, suppose you are going to be a system analyst, either a communication system or any control system, where the dynamics is happening. Things are changing over the time, which is not able to predictable, or which can be predictable, and there is a randomness in it, or there is an uncertainty in it, which can be predicted. And if you have a quite good knowledge in probability and stochastic process, and of course quite good knowledge in the statistics, then you can be able to forecast. You can be able to make a nice predictive model based on the knowledge of stochastic process. Not only stochastic process, you may need probability as well as statistics. And some people may little confuse with the probability and statistics. Probability in the sort of the theoretical side, whereas the statistics is with the data. So you have the information in the form of data, you analyze it, then with the probability concepts and so on. And if you have quite good knowledge in stochastic process, then the prediction is or the predictive model can be created by you, and you can feel it how much stochastic process is used. And any other yes, I missed this point also. That's correct. So in the insurance, if you have a quite good knowledge in probability and stochastic process, how many um, how many people are asking for claims? Usually we make it as the making very strong assumption. We say it as a Poisson process, and whereas it is not a Poisson process. The rate in which the people are asking, putting the claims to the insurance company, that becomes a time dependent, and that rate we can treat it as a constant. We can make an easy model. Actually, that rate is a time dependent as a function of time, and that can be considered as a stochastic process. And one can study the stochastic process related to the rate of the public or the insurance holder is making the claims. This is one side. Whereas the other side, the insurance company side, how much they can get the profit if they make a nice plan, or if they make a certain amount of premium and certain rules, then they can maximize the profit. And this is going to be a sort of stochastic optimization problem, because they may not know how many people are going to be insured, and how much money they are going to pay, and they may not know how much they are going for the what do you call this claim, how much they are going to claim, and how much they are going to take a new policy, and how what is the duration, and what was the age of the people, and so on. So there are many uncertainty. And, therefore, the stochastic optimization problem of maximizing the profit in the insurance company side, that's also need a stochastic process knowledge. Any other topic you would like to ask the question? I'm just checking the screen. Any other concept where the students ask in the forum for the debate last few minutes? Okay. So our TA's suggestion is you should actively participate in the discussion forum, so that we will come to know what was the issues by you, not only by you, by raising by you, the others also will come to know that, and we, when the way we answer, that way it will be clear to everyone. Right? Any other question to be asked? So is it audible and are you able to follow what I'm saying? Please, somebody raise the chat, then I can know it. Any question you can ask related to the course. Yes. Can you elaborate on bit error rate? Is the work to our course? No. So the bit error rate. Okay, since I use the word rate, so you may be interested in bit error rate. If I'm not wrong, bit error rate comes in the communication system in which the packets are transmitted from one node to another node, and some of the packets are dropped because of maybe the reason, and packets are not transmitted, that we treat it as the error. The rate in which the packets are not transmitted due to whatever be the issue, with the rate in which the things are happening, that they call it as a bit error rate. I'm correct? Yeah, not happening. Is it correct? It seems to be. Yeah, there is a some lead time, so please take many seconds to for them to reply. Yes. Okay. So, in the communication system, what they do is they keep the bit error rate as a constant. But actually, the rate means it's a per time unit. It could be a millisecond, it could be second, it could be minute, or it could be hour, whatever it is. So what happens is it's a sort of inverse problem. We can identify for a given this much rate what is the how many packets are lost. So in the problem can be put up in both ways, and by we call it as a sensitivity analysis. By varying over the rate, we can identify what is the optimal rate in which we can maximize the throughput. So, but as far as our this course is concerned, the bit error rate is away from our complete stochastic process. But still, based on my knowledge with the communication system, I am answering. But it can be studied separately. But the probabilistic knowledge and the stochastic process knowledge is going to be very useful to fix the rate or to study the bit error rate. So with this, let me stop related to the bit error rate. I'm just coming to the next question. How does stationarity varies if a random signal passes through LTI or non-LTI system? How does stationarity varies if a random signal passes through? How does the stationarity varies? Okay, that I think only the electrical engineering people can answer the question. And for us, I'm just giving an example. The systems, the signals can be considered as the stochastic process, and that's a quite good application. But how the stationarity is, varies in the signal and so on, that is very difficult to bring a time invariant. Okay. So that only electrical engineering can be able to answer these two technical questions related to the signals. But for us, it is a given stochastic process, given probability distribution, and we verify whether it has the stationarity property or not. So we won't comment on how the signals have come and how it is calculated and how it is observed or computed, that is beyond discourse. You please remember that I am a mathematician, not the engineer. Engineer. Any other question? Effect on? No, it's beyond the level of me to comment. Please read. Some books are there with the signals and systems itself. They start with some example of our stationarity property, whatever we discuss and so on. So please go through some of the books in electrical engineering. I think even the book's title is called the signals and systems. Or you go to our ADDL website of the course, so which has the same contents. Any other? Okay, thank you, sir. Thank you. Any other general question? How the course cope up, or what way you are feeling difficulty, which can be reduced over the period? The student who asked the examples of stochastic process, this live session is also a stochastic process example. Number of students in the live session, that's a random variable. So even though over the time is 1 hour, number of students in the live session, that form a stochastic process. Okay. Okay. Random process. Okay, so some students, but those books that, okay, the books which I said, okay. So there are some elementary books. I use it for the setting the paper after I know that. There are some books I have seen it, which has a very good easy examples with this functionality property and left it's more. You put some more effort in it. Okay, I think the next question. Not Oppenheim, some other book. Maybe if you write a mail to me, I will answer them. I will reply them. Next question is by Saurav Bharadwaj. The deadlines for submitting the assignments is a bit difficult. Okay. For looking at a question like me, I hope some relaxation is given to people like us. See, this is an online course. If you start giving the relaxation for different things, then there is no end. And there are many people, they do the similar courses in, I'm not going to spell out the websites. There are many websites and similar online courses are there with odd deadlines. So there is no soft deadlines. Then only you can put the effort and make it. So I feel there should not be relaxation, and we should put some effort. And its weightage is only 25 marks. So therefore, by keeping all these things in the picture, we have made 25 marks for the assignment part and 75 marks for the final exam. You can make it. Don't worry. Any other question? It's possible. I understand. Thank you for any comment. Yes. Thank you. Yeah, I know that you will have a tough time to submit the assignment and so on. But the thumb rule, which I feel, when the assignment is a pop up, you should go through the assignment. Then you should keep doing the problems over the period, not in the last day, last minute. In my whole life, I never had the habit of last minute, last work. So I feel one should have a working culture of a little bit daily or sometimes. Therefore, you can go through again and again in your mind. Therefore, you can do it better. So, please do. Application of Marco chain. What are the physical application of Marco chain? Marco chain has a lot of applications. Based on the Marco chain logic only, there are many predictive models they make it. Even in the hidden Marco model that has the application of discrete time Marco chain. And many of the companies, if they want to decide some resource, they go with the Marco chain concept. Uh, I have plenty of examples.
Google search, only looking for media to order increasing the page, has application of
Correct. So my TA, Mr. Puneet is giving the immediate example. In the Google screen, whatever the ad is coming, whatever the computers you are using, laptop or desktop, and the ads are coming based on the Markov chain logic. That means what you will expect to see in future, given that you have seen recently this and so on, not the past. No, the ad won't bother which the Google won't bother which ad to put. The one which you have seen last year or 2 years back. But whatever the recent website you have browsed, they will put the ad that as the immediate. So that is application of coaching. Like that, there are many more applications you can think of. That means the future depends only on present, not past. That means you whenever you want to design something, whenever you want to go for something, you can have a future is going to be most probably this, given that this is a current trend, not the past. And just giving the words. So this same thing can be captured in a mathematical way. Our whole course is going in a mathematical way, but the fundamental concept is this one. Next question is Markov chain can be applicable only for those events which are based on dependent sequence of occurrence. Yes, Markov chain is nothing but the first order dependent stochastic process. So there are some stochastic process may not have a dependent at all. They are called independent stochastic process. There are some stochastic process may have a dependency over few past information, including the present. Then we call it as a AR model, autoregressive model that we are going to study little later. Whereas the Markov process is the particular case of dependent process, that too first order dependent process. That means that it depends on only one recent information, not the past. So whenever you have that assumption, then you can create those type of example you can think of as an example for Makuchi. If that assumption violates, then you cannot take it. So sometimes even that assumption, even some of the application does not have it for the sake of mathematical study, for the sake of mathematical pattern, we make the assumption we study via Markov chain by imposing the Markov property. Right? What I'm concluding is that there are some applications it always satisfies the Markov property. There are some applications it may not satisfy, but you impose as the assumption, then it's is it clear? Are we losing any information if we choose order of dependency? Yes. Whenever we like first order only, yes, that's correct. by making this assumption, we are losing some information. For example, one particular stock price, if you want to study the next day price, may depend not only today's price, may depend on the last 2 3 days price. If I make assumption, That means that I am just removing the information about it does not capture in the next day price depends only on the present day, not the past 2 days information. That means I am losing some information. Yes, it is correct. We are by making assumption of macro property, we are losing some information if the system is having some more order of dependency. Any other question? Is it clear to you now, Abhishek Bhatia? Fine, thank you. Okay, so we have 3 more minutes. Is there any other query? Any other question? Rapid. So first, I should thank my both the TAs, both are my BSc students, and whatever we are progressing because of them, not me. Because I always give some ideas and they execute. Sometimes they come up with very new concepts. Why not we can test things and so on. So the credit goes to my both the TAs, and as long as I always say that as long as at least 33 people get benefit out of something, that's okay. So whatever we are doing, that is worthwhile for our country. Okay. So please raise the issue, whatever you are having a difficulty with the discussion forum and so on. Yes, ask the questions so that we will also improve. The way you ask the question, you will think, okay, we made a mistake, we will correct it. Still, if at all any mistakes in the assignment sheet, we will fix it. So just raise the issue, then accordingly fix it. Similarly, some lectures also, maybe I would have said orally infinity, but I would have written number here. So some of the mistakes we are not able to fix it. So please bear with us for our mistakes which we could not able to fix it. Fine. If no other query, we thank all the 20 viewers and thank our TAs and thank the NPTL in Delhi as well as NPTL Chennai for this good show. Thank you.